Good afternoon and welcome to the Sustainable Materials Management webinar series, a joint effort between the National Recycling Coalition and the Pennsylvania Recycling Market Center. My name is Wayne Bowen and I'm the Program Manager for the Recycling Market Center and will serve as your moderator today. We would like to extend a special thanks to Bob Hallis of the Mobius Network for providing the webinar management software for this series, and Lisa Ruggiero of the National Recycling Coalition for providing technical support. Today's webinar focus is on aerated composting systems. Following the presentation, we will conduct a question and answer session. If you have a question or comment, please use the GoToWebinar dialog box located in the control panel on your screen. You may also use the dialog box to request assistance if you are experiencing technical difficulties during the webinar. Please note that this webinar, like all the webinars in this series, is being recorded and will be made available as a YouTube video. Links to these videos can be found on both the National Recycling Coalition and Recycling Market Center websites. And now I'd like to introduce our presenter, Peter Moon. Peter is President and Principal Engineer of PME/O2 Compost and is a licensed professional engineer in the state of Washington. Peter has a bachelor's degree in geology and a master's of science in geotechnical engineering from UC Berkeley. He has 25 years of consulting experience focusing on composting for the past 15 years. Peter works with nearly every variety of organic byproduct. However, his principal areas of interest are composting horse manure, grape pumice, golf course green waste, and exotic waste such as zoo manure, mink waste, and farm mortalities. As an adjunct to teaching the composting process, Peter also works closely with vermicomposters and compost tea users. And now I'd like to hand the program over to Peter.
Thanks, Wayne. I need to update that introduction. I'm a consulting engineer, again, in Washington State for about 33 years, and I've been in the composting industry for 26. So I guess it's been a while since I wrote that. Before we get started, I too would like to thank a few people, Pennsylvania Recycling Market Center, for hosting this event, and Wayne in particular for organizing things on the behind the scenes. In addition, Melissa Pennington with the US EPA to help promote it. We're going to be giving a webinar with US EPA next month looking specifically at on-site composting at universities, so I'm looking forward to that. And most importantly, I'd like to thank all the folks who have joined us here today for taking time out of your schedule to listen in for 45 minutes or an hour and hear what I have to say about aerated composting. As composting goes, I think aeration is really key to our success, especially when dealing with more challenging materials. Let's see. Can you see that on site? Okay. Events such as this help us to get the word out, which is great. So my objective for today's meeting is to demonstrate through a series of examples that composting is a viable strategy for waste reduction and for resource recovery. And my goal for you is to take action to further compost in your region of the country. As an introduction for who we are and what we do, O2 Compost specializes in compost system design and operator training. We work with all varieties of organic waste materials and all scales of operation. Examples would include large regional composting facilities with an effective radius of 100 miles or more, medium-scale facilities that support a local community, both of these dealing primarily with municipal solid waste streams. And then we also look at on-site compost systems typically for universities, prisons, military bases, and the like. All of our compost systems utilize the aeration, aerated static pile method of composting, and that's what we're here to talk about today. By inducing airflow into the compost pile, we're able to optimize the biology of the system, expedite the composting process, produce a safe product that's free of pathogens, parasites, and weed seeds, protect surface water and groundwater quality, as well as control odors and vectors, and ultimately produce produce a finished value-added product. So with that, we start with raw feedstocks of all varieties, in this case food waste, and we put it into a system, in this case a freestanding aerated static pile as an example. There are many different ways to do this, and I'll be showing examples of that. And our ultimate goal is to produce a high quality finished product. Today's webinar, we're going to be looking specifically at aerated static pile or ASP composting systems, composting principles and parameters, step-by-step flow-through composting as a series of slides to show an example compost systems for agricultural, institutional, and municipal systems, and then my suggestion, if you choose to take action, how to get started and utilizing a pilot project. At the end, Wayne and I will be fielding questions from the audience. So what can be composted? Organic wastes or natural resources? This is a philosophical breakwater that I'd like you to consider. Agricultural waste, livestock manure, zoo manure, crop residuals, waste feed, punch waste, mortalities on farm. And this is a photo as an example of Bailey Compost in Snohomish, Washington. I helped set this up in the early 90s, and this became a municipal compost system that now processes on the order of 30 to 35,000 tons of municipal waste per year. Municipal institutional waste, green waste, food waste, which has really become the mainstay in the future of the composting industry. Biosolids, septage, night soil. I had an opportunity to deal with night soil in Beijing, China. Garbage and roadkill. Industrial waste, fruit pumice, vegetable culls, fish waste, like you see here. The Northwest has a burgeoning aquaculture industry, milk byproducts, and nursery waste. Here's an example of food waste. When people say food waste, they seldom know what they really are referring to. This is out of a Walmart store in Syracuse, New York at the Amboy facility. And this was a first experience for me to have basically vegetable soup show up to the site. And I'll tell you, when it comes to the site, you better be ready to deal with it. It can be a problem waste. So definition of composting: transformation of raw organic materials into biologically stable, humus-rich final product that is stable, free of pathogens and plant seeds, and can be beneficially applied to land. There's lots of different definitions for composting. Some are very expansive, some are very short, but I think this is probably a pretty good working definition for today's discussion. Alternative methods of composting, starting with simple and giving you examples through more complex systems. This is a large non-aerated static pile. It's a facility in Utah that I am currently working on, and we have a pretty significant concern about fire, which is a topic of conversation. We're going to be breaking this pile down here shortly to avoid a catastrophic event. Here's an example of a turned windrow system. This is the Woodland Park Zoo in Seattle, Washington. As you can see, looking into the picture, the piles are getting progressively darker. This is as the straw and hay and feed are breaking down and the manures are converting over. What you can see in the back is a darker, more uniform appearance. These piles are being combined and ultimately sold into the community. We think of composting, or a lot of people do, as a turned windrow process using large equipment. This is not a particularly effective means of composting, as I will describe later. This is also a turned windrow system where you have a tractor pulling a windrow turner here and a water tank. This is in Salinas, California, where it's really quite dry, and so the addition of water to each of these windrows as it's being turned is really quite important. This is an example of a pilot project that I worked on with the Onondaga County Resource Recovery Authority in Syracuse, New York. The day after we constructed this pilot project, it snowed, and it didn't stop snowing for about 4 months, and we were able to continue composting quite effectively throughout that period. Here's a couple of examples of small systems. These are aerated bin systems for horse farms, one in our local community, Snohomish, Washington, and one in North Carolina. We have about 1,000 of these out and about throughout the country, U.S. and Canada primarily. A couple more examples. These are aerated bins and bays. The one on the left is a mink farm in Abbotsford, British Columbia, and the other is a horse farm. Looking at different means of aeration, this is a biosolids composting facility in Oregon, where we're, instead of pushing air into the pile, we're actually drawing air through the pile negatively and then collecting that air stream and running it through a biofilter. I'm not sure what to do about that. Apologize. Running it through this biofilter off to the side for odor management. This is an example of a system that's referred to as the Compost Factory here in Washington. Fully enclosed, highly controlled system. The piles that you see outside, these are all biofilters for odor control and mitigation. Since this system was constructed, the community has continued to develop to where it has 2 schools, a community of homes, businesses, and an old age facility. And so it's really critical that they control this entire process quite closely. This is another system. As you can see, it's getting more advanced. This is in Washington State. We did the design and permit work, and Engineer Compost Systems did the aeration infrastructure. It starts in aerated bays, both positive and negative aeration, and then after 24 days it is moved into an extended pile where it is being turned by the windrow. Lisa, if you have any suggestions on how to quit doing that, I'd appreciate it.
Sure. The next time there's an option that says something like accept and don't show this message again, I think it's
okay.
The lower one, so try clicking on that.
Okay, thanks. This is the inside of the bay. Each bay holds about 500 cubic yards, and air is delivered in trenches. These also act as drains. There are wired temperature probes that connect to a computer system that enables the operator to adjust the airflow both in terms of volume and in terms of direction, so it can pull air through the pile or push air up through the pile. And here's another example of the biofilter that sits out back for odor control. This system's been running for, I'm going to say, 6-7 years now, and they have not had an odor complaint from the local community. So those are some examples of aerated compost systems. When we talk about aeration, it's not just one thing, but the principle is that we deliver air to the material. And so looking at a very simple schematic of a compost pile, we have raw organic materials, minerals, water, microorganisms. You really don't need to add any magic potion to this to get the composting to take place. The microorganisms are there. Let's see.
There you go.
Which one here?
Yep.
Okay, we'll see if that works. Thank you. So we have the raw mix here. The key is, and I'll talk about this, the nutrient balance, bulk density or porosity of the mix, and the moisture content. We add oxygen to the system. The byproduct of the microbial activity is heat, water, and carbon dioxide. And over a period of time, we are converting this raw mix into stable organic matter, minerals, water, and microbes. And it's the microorganisms that are the secret to the beneficial use of compost. That and the organic matter that brings with it tremendous advantages to soil quality. So the three critical parameters are, again, our carbon to nitrogen ratio. Our target is 30:1. These sorts of rules of thumb are things that composters love to talk about and argue over, because the deeper you go, the more undefined things become. But this is a general rule of thumb: carbon to nitrogen, 30:1. Porosity, which is a volume of void space in the mix. We can measure this a couple different ways. Through the bulk density, we're looking at 550 to 950 pounds per cubic yard. In free air space, 35 to 60%. There's a very simple field test that you can use with a 5-gallon bucket and a scale to determine these parameters. And moisture content. With an aerated compost system, we want our initial moisture content to be on the order of 60 to 65%. And it feels wet, but it doesn't have enough water that it's going to drain out of the bottom of the pile. If you squeeze a handful of it, you may be able to get a drip or two or a bead of water to form between your fingers. Water is critical to the composting process. So the secret to composting is oxygen. Will this be on the test? Absolutely. Oxygen depletion in a compost pile. If we aim at a 10% oxygen level throughout the pile, we are said to be in the aerobic zone, and we're going to be encouraging aerobic microorganisms. Below that line, or 8 to 10%, we're dipping into the anaerobic zone. The anaerobic byproducts are typically very smelly, odorous gases. During the early stages of composting, when we induce airflow into the pile by turning or with an electric fan, we're able to bring the oxygen level up to roughly what we breathe at sea level, slightly over 20%. But when the blower stops or when the turning is complete, the oxygen level will drop off very quickly, such that we return to the anaerobic condition with anywhere from 20 to 45 minutes, as shown here. As the pile continues to compost, and over time, this will tend to flatten out, where it takes longer for us to get back to anaerobic composting, but in fact we do return there. So any static pile that you see out there, the core is going to be anaerobic. So with aeration, it allows the operator to maintain aerobic conditions, mitigate impacts from objectionable odors, and this is a significant benefit with aeration. I was recently, earlier this year, in New Zealand, working on a large municipal project where their chief issue was odors. And by converting from a turned windrow system to an aerated static pile system, we were able to mitigate all of those problems and neighbor impacts. We're able to manage pile temperatures by controlling the frequency and duration of airflow into the pile, reduce the loss of nutrients, expedite the rate of composting and curing, and produce a superior compost product. There are many other advantages, but these are really the key ones with aeration. So to look at the composting cycle, or the life cycle of a compost pile, we build it, we initiate the aeration, and we immediately are in what's referred to as the active phase of composting here. This is the mesophilic range, which is below 40 degrees Celsius. We quickly enter the thermophilic range, which is above 40 degrees, our goal of which is 55 degrees Celsius, or the equivalent of 131 degrees Fahrenheit, for a minimum of 3 days. And with meeting these criteria, we are destroying pathogens in the mix, and we find that we're also destroying parasites, weed seeds, fly larvae, and so forth. Our goal is to stay below 70 degrees C. As you can see, this has gone somewhat higher. And so we're controlling airflow to adjust this heat. At these high temperatures, we are limiting the type and number of microorganisms that are doing the work for us. And because compost is so self-insulating, once we get up to those high temperatures, we tend to keep them. They don't vent off very readily at all. So we need to do that mechanically in some way, either with aeration or turning. As we progress through the life cycle over time, after 2 to 3 weeks, the pile temperature will naturally start falling off, and we enter what's referred to as the curing phase. The active phase is primarily a bacterial-driven process, and the curing phase is primarily a fungal-driven process. And this dashed line simply represents that it's a transition between the two. It's not a distinct boundary. This is what real data looks like. You can see when we initiate aeration, the pile temperature climbs very, very quickly. We can often see 40, 50, 60 degree temperature differentials within a 12-hour or 24-hour period. And then they will drop off over a period of time. I've arbitrarily dropped this line in here to distinguish what I would call the active phase from the curing phase over here. So what I'd like to do now is go through a series of slides that demonstrates aerated static pile composting as a concept using a bin system, a 3-bin system, as a specific example. So in this case, this is a horse farm. It's one of our systems, what we call a top-down system. The manure is delivered into one of these 3 bays from behind and then later taken away from the front. This bay here has a concrete floor. This is for storing raw mix coming in or finished product ready to go out. You can see here the blower that feeds air into the manifold. There's 3 pipes that come off of this manifold, each with a valve that allow us to direct the airflow to any one or combination of these bins and to control the volume of air that goes to the bin. This is what the floor looks like. Concrete floor with a ledge built into it on 2 sides, over which we span it with 2x6 lumber in this case, with a prescribed 3/8 inch gap between the boards. This allows us to distribute the airflow throughout the mix and but it also gives us a concrete ledge to get in with our front end loader and not clip the boards. Question will come up, doesn't material get down in there? It does, but it doesn't pack so tightly as to prevent airflow. And the blower has plenty of pressure capacity to overcome any obstruction that might fall down in there. So looking at the same thing schematically, we've got the 2 trenches here with the air pipe delivering air. These are the boards, concrete in our walls. This is a shaving type material which is porous and acts as a filter, so the finer material tends not to get down into the gaps between the boards. We fill it over time. In the case of a horse farm, we will try to fill it in a period of 25, 30, 35 days and moisture condition it as it's going in. Again, our goal is to be 60 to 65%. When we are near the top, we put a compost cover on top of the raw mix, and this serves several purposes. It acts as a thermal blanket such that all of the raw material will come up to 131 degrees Fahrenheit for at least 3 days. It acts as a biofilter for odor control. It also absorbs volatile organic compounds and ammonia, and given that those are nutrient-based, we are retaining nutrients, nitrogen primarily, in that top layer. It as I said, retains nutrients. It also serves for vector control. Any fly larva that is in the mix here will cook and die. And because this is a stable material, it does not attract flies to it. Flies on horse farms can be a huge nuisance as well as a health issue for the horses. Helps us retain moisture. I mentioned moisture is really critical, and because this outer layer here can dry and we can re-wet it with a hose from time to time, we tend to retain our moisture in the mix itself. And it improves the general aesthetics of the manure handling system. So once it's full, we initiate the airflow into the system with a volume of 10 or 20 cubic yards. We'll typically go with an on cycle of about 2 minutes and an off cycle of about 30 minutes. And again, our goal is to maintain aerobic conditions throughout the pile. No turning throughout this process, so it makes it fairly straightforward and simple to allow the timer and the blower to do all the work for us. When we induce airflow, we will produce a tremendous amount of heat. Our goal, again, 131 degrees Fahrenheit throughout the pile. We will see higher heat in the core of the pile. And so we allow that to take place, even though it doesn't optimize the biology. But again, from a practical matter, from a practical standpoint, our objective is to produce a safe product. When the blower kicks on, it's not at all unusual to see steam coming off the pile, and the odor of that steam is really very, very mild. You can tell that good things are happening. Over the period of about 3-4 weeks, you're going to see volume loss, typically 25 to 40%. In the case of a horse farm, it's a function of the bedding. So if it's a shavings-based material, you're going to get less volume loss. If it's wood pellets or a fine sawdust, you're going to get more. Here's a series of photos of cleaning out the stall. We take out the wet sections and the manure. We lift the manure out, leaving as much bedding behind as we can. In this case, she's adding water from the bucket on the wall to moisture condition the material before it goes in. This allows the mix to absorb it. It's very, very difficult, if not impossible, to wet down an entire pile simply by spraying it on the outside. Dry organic material becomes hydrophobic. So what we do here is by wetting the mix going into the system, we're allowing it time to absorb into the fibers and into the cellular fraction of the manure-based material. She's adding it to the bin, and here she is adding compost to the top and raking it out, and you can see the difference in color between the finished product on top and the raw material below. Within 10-12 hours, you're going to see very high temperatures very quickly. And so that's kind of the bin procedure. Now, in terms of a flow-through process, what we will do is fill the first bin, turn the air on, and begin filling the second bin. We will then proceed by putting on the cover when the second bin is full and start adding manure to the third bin. And in that time frame, we will have gone through most of our active phase of composting, at which time we remove the first bin and we simply set it up to start receiving raw material. So in this way, we have a 1-2-3, 1-2-3 flow-through process. Now, looking at the same concept in a larger scale with an aerated static pile scenario, and by the way, this is where aerated composting first came about. It was back in the early 70s in Beltsville, Maryland. It was under grant with the U.S. Department of Agriculture. And through trial and error, they came up with this approach and methodology. So looking at this photo here, we've got our blower. We feed air into a manifold here. It splits the air and then divides it down these lateral pipes. This first section of pipe is solid. This next section is all perforated. And then we end with a solid pipe and caps. This is our aeration zone right here in the center. So over the top of that, looking at this in cross section, We have aeration plenum material, which is a wood chip or something that is structurally sound but very, very porous. This allows the air to distribute across the floor of the pile. Over the top of that, we have our mix here, this light gray. And then finally, we put a layer of finished compost over the top. And oftentimes, I'll work with composters who neglect to put this finished cover on. And they very quickly realize that it is a critical aspect to the design. It's not something that should be left off. Again, it acts as a thermal blanket, a biofilter for odor control, vector barrier, helps control moisture content, and produces a uniform appearance to the pile. So looking at these schematics in a real picture, this is the blower, timer to run the blower, our source of power here. Air is delivered through the pipe, it splits and then runs down through the pipe in the aeration zone. Now you can combine these side by side to form what is referred to as an extended aerated static pile or an EASP system. So you can see here we've got 4 blowers, 4 manifolds, 4 sets of lateral pipes, and over the top of that we are combining or constructing our entire pile, which is represented here. By not having individual piles but going to an extended format, we are able to greatly increase the volume of compost material per square foot of available space. Typically we will see, when converting from a turned windrow system to an extended aerated static pile system, 4 to 5 times the volume per square foot of available space. Here's an example at Bailey Compost here in Snohomish. This is a 4-zone system. Each of these are 5 horsepower blowers delivering air into this pile. This pile measures about 80 feet in length in this direction, 140 feet in width, and it started out to be about 12 feet tall. There's about 3,500 cubic yards per pile. And just off the site, you can see a second pile. This one is being deconstructed, getting ready for the next batch. So this is what I refer to as a batch flow-through process. So looking at a typical turned windrow system, this was one I worked on for Upper Valley Disposal Service way back 1992 and 93. They converted this system with this extended aerated static pile. This was our pilot project, and then ultimately to this system where these piles, this is grape pumice from the wineries. This is an annual batch process. These piles are 100 feet long, or 100 feet wide rather, 550 feet long, and they too start out around 12 feet tall. On each pile there's about 25,000 cubic yards, and they're operated by 10 blowers, so there are 10 zones. Each of these blowers is operated by a programmable logic controller, and once it's constructed, the owner is hands-off. It just operates itself. So you can see by these examples that aerated static pile composting is hugely scalable. So pilot projects, looking at a series of examples. This is at Washington State University Cooperative Extension. These are micro bins, what I call micro bins. This is a product that O2 Compost offers. And in this case, they're looking, doing research for King County and Metro, looking at biosolids composting. They've also been doing research on fate of antibiotics and pharmaceuticals, and most recently they have been composting mussels out of the aquaculture industry. This is a project, a bin system in Beijing, China, outside Beijing, China, and this is all food waste. They're laying it out as a means of drying it, and you can see if you look closely how much contaminant plastic there is in there. It's a huge problem. They did a beautiful job building this system, and you can see here solar panels. This is all off-grid aerated composting, aerated bin composting. I'll talk a little more about operator training. I've been involved over the past 12 years with the Washington Organic Recycling Council annual operator training class. I would recommend to anybody to attend a class like this. At the class, we have hands-on group exercises, and we also demonstrate aerated static pile composting fish. Each one of these bins weighs 1,000 pounds. It's filled with dead salmon out of, these are mortalities out of the fish farms in Puget Sound. We ran it through a manure spreader with a combination of bulking agents, yard debris, and fair waste out of the local fair. Here's our aeration system, again, blower, manifold, lateral pipes. This is the perforated zone here. Building the pile over the top, and then ultimately covering it with, in this case, we did not use finished compost, but rather raw feedstock, but it did still serve as a biofilter for odor control. And believe it or not, nobody even could tell that there were 3,000 pounds of fish in that pile. Oh, and here we are congratulating ourselves for a job well done. Another project some of you may be familiar with Ned Foley at 2 particular acres in Pennsylvania. Ned came out many years ago and met with me, took a tour of sites in Washington State, and then exported all of that information to his farm in Royersford. It has since evolved to an extended aerated static pile, much like the other examples that you've seen. He loves to show this picture because these are million-dollar homes on the back, and all of these folks love Ned because he has resolved his odor issues, and I think behind the scenes also provides them with free compost. But don't say I said that. In this particular case, he's using high-density polyethylene pipe. These are thick wall pipes, and he grabs onto it with a chain, pulls it out of the pile with his tractor. So that may answer a question you've been asking yourself: how the heck do you get the pipe out of the pile without breaking it? In this case, he's been using the same pipe for many years. Another question that comes up is, can you compost in cold weather? Absolutely. These piles, as you can see, the snow is not on the piles, and if you go in 1 foot or 2 feet, even if it's frozen on the outside, it will be nice and toasty on the inside, composting. This is a picture of his compost on the side, and Ned taking temperature readings. Last year we were involved in a really interesting project looking at reduction of volatile organic compounds with extended aerated static pile method using solar power as our sole means of power. With this project, I should mention it was the host facility was Harvest Power excuse me, in Tulare, California. Tulare, California is near Bakersfield, and if you've never experienced 115-degree weather, I recommend you go there about this time of year. It was a funded project, grant funded through the San Joaquin Valley Air Pollution Control District and their Technology Advancement Program. This is a picture of the facility with our first zone completed. These are our solar panels. All of the inverters, batteries, and so forth are in these cabinets. In this case, we used 1.5 horsepower 3-phase blowers. We had completed this pile, and we're getting ready the following week to construct this pile. I should mention, when we were constructing these piles, we were at the same time constructing turned windrow zones with this same materials. So we had a direct comparison in terms of time and materials. Each of the 3 zones were constructed in weekly intervals. You can see here we had zone 1, with Zone 2 then laid on the advancing flank of Zone 1 and finishing with Zone 3 here. In cross-section, we have our 4 pipes. This is Zone 1, Zone 2, and Zone 3. Piles were about 7 feet tall to start with, and each one was in the neighborhood of 500 cubic yards per zone. This is the pipe, plenty of material over the top of the zone. We actually constructed these piles using a potato conveyor. Kevin Barnes with City of Bakersfield came up with this idea, and it worked extremely well. This conveyor extends out, it telescopes out, it moves side to side remotely, and as well as up and down. We used a material handler to feed a Comptech slow-speed shearing equipment. The shearing equipment fed a hopper here, which then delivered the material onto the belt to the end. And as you can imagine, at 115 degrees, it was very, very dry. And my biggest concern over the entire project was, can we get the mix wet enough, and can we keep it wet enough throughout the trial period? And fortunately, we were very successful at doing that. So again, here's a look at the finished Zone 1 system, photovoltaic panels, the solar apparatus in the cabinet, the blower, manifold. And this pink ribbon, you may be asking yourself, what is that? I called it our no man's land. We cordoned that off to prevent anybody from going in there and compacting or otherwise disrupting that area, such that when all 3 zones were complete, the team of experts came in and conducted flex chamber testing, which is a means of grabbing representative air samples from the pile, from the surface of the pile, and then sending those air samples off to the laboratory for testing. So they did a lot of on-site testing. To me, it looked a bit like a garage sale, but the results were quite interesting. This project, comparing a turned windrow system side by side with an extended aerated static pile approach, demonstrated a reduction in volatile organic compound emissions by over 95%, reduction in NOx emissions by 88%, ammonia 70%, and we were actually able to reduce water consumptions comparing the 2 systems, aerated static pile and turned windrow, by 55%. If anybody is interested in the group, you can email me and I'll send you the link to the report, which goes into great detail as to the benefit of ASP composting. So then the question is, what's our next step? First, I would suggest attending a training class. These are some examples. The U.S. Composting Council has an annual conference this year. It's in the end of January. It's in Oakland, California. You can attend any number of workshops on a variety of topics of composting. They have introduction to composting, what I would call Compost 101. I do a day-long workshop on aerated static pile composting. There are many other experts who look at the business of composting and in a variety of different topics. It's a it's probably my favorite event and venue of the year as it relates to the composting industry. The U.S. Composting Council also sponsors a 40-hour regional training program, and they have it at different locations around the country. Washington Organic Recycling Council, or WORC, also conducts a 40-hour compost facility operator training class. It is in October, begins this year, October 14th. It's all week. I will be one of the presenters and trainers at that event, and I believe there's still time and space available. It does sell out every year. I also do a 3-day hands-on workshop training class, which takes the principles of composting and puts you in the field actually constructing a project, monitoring the system, and learning everything there is to know from a hands-on perspective. That's going to be coming up here in September. We also tour 4 other facilities, some of which you saw in the pictures earlier. So training is very important. There are many other training classes as well. If you get on the internet and do a search, you'll be able to find several. There's one in Texas, I believe. I know there's one in Maine. So wherever your region of the country is, I would recommend it that you attend one. So the next step also would be conduct a pilot project. I love pilot projects because it gets us past the point of making a decision. Can we do this? How much is it going to cost? How big does it need to be? With a pilot project, you have a defined schedule, a beginning, an end, and it really helps limit the risk. People are risk averse. It's inexpensive, so you can do this on a fixed budget. It helps you to compare alternative technologies on a small scale. Of key importance, it helps you sort through the logistics of handling feedstocks. How do you divert them? How do you collect them and transport them? What do you do when you receive them? Everything that is upstream of the composting process. And this is a real shakedown cruise for a lot of people. They think, well, we'll just get food waste. No, it's not that simple. We're able to demonstrate the ASP method to various stakeholders such that they can say, hey, it doesn't stink. There aren't a lot of vectors. There's no runoff. All the things that they were afraid of, they can see firsthand, wow, this does work. Here's an example of a couple different systems. I showed you the one earlier with Washington State University, our micro bin off to the side here. Simple plywood boxes. They work great. For a budget of materials of about $100, total cost of about $1,000, you can be set up and running. And similarly with tongue and groove, larger system, tongue and groove lumber, a little more money, you can do the same thing. So pilot project allows us to gain hands-on experience, train operations staff so that they can understand on a small scale how this works. Develop compost mix recipes, learn how to receive and mix raw feedstocks. If you're dealing with something that is putrescible like food waste or fish or mortalities or any of these sorts of things, you really want to be ready for it when it arrives on site. You don't want to have to ask the question, now what do I do? You learn how to construct the pile, monitor and optimize the composting process. You're also able to, with an example system, determine which permits might be required. On a small scale, typically they aren't, but on a large scale, they very likely will be. Establish confidence with the regulating agencies that you're not just embarking on a dangerous mission here. Produce a finished product for lab and market testing. This is a great way to validate that, yes, we can convert a raw waste material into a value-added product with many, many benefits to it. Established a design basis for full-scale composting facility. Oftentimes I'll work with people and they'll say, well, how big does it need to be? Well, it's a function of the volume of material that we're working with. And once we go through this pilot phase and perhaps do a waste audit, we will have a much, much better handle on the volumes, tonnages, and ultimately the size of the system. It will also help us develop a reasonable cost model for capital investment, operating costs, profit and loss projections, and return on investment. In any group, there should be a bottom line oriented person, and this will help us really answer their questions. Pilot project is a precursor to a feasibility study. With a feasibility study, my experience is you're guessing all along the way. With a pilot project, you can answer many of the questions that should come up in a feasibility study. So if you do an FS, this is a good precursor to that. And ultimately to make a go, no-go decision quickly and at minimal cost. So a lot of people like to go with a pilot project, and we do this as part of our business as well. So that's pretty much what I had prepared for the discussion. Thank you very much for attending. I appreciate the opportunity to share some of this with you. There are many, many resources available at your disposal. I would suggest one, our website, and feel free to contact us through the Contact Us portion of the website, or give me a call or send me an email, whichever you prefer. So Wayne, at this point I'll turn it back to you, and we can open the discussion up to questions and answers.
Okay, thank you, Peter. A very excellent presentation, and the graphics and photographs were very helpful. Good addition to the presentation. We're now going to field some questions from our presenter, for our presenter. Again, if you have a question, please enter them onto the GoToWebinar dialog box. And we do have a few questions queued up here already, so I'll start off. This question has to do with negative aerated systems. The person noticed there was not a biofilter attached to this system. Are there any odor issues with negative aeration systems?
Actually, with every negative aeration system, there is a biofilter. So let me go back, if you'll allow me to go to a particular picture. I'll show you. Let me scale this down here. Oh, where am I? When we draw air here, with this system, I mentioned that this is an engineered compost system where it is computer driven, and each of these bays we can push air up through the mix or pull air down through the mix. And we do that through these trenches, and behind the system we have a biofilter. So with all negative aeration systems, we do deliver air to a biofilter as a means of controlling the off gases and mitigate any impacts from odors. I should mention, with negative aeration, there are some other challenges. One, by pulling air out of the pile, it's hot and it's saturated. And when we do that, and that air goes through these pipes, these stainless steel network of pipes, it cools down. And what we find is we produce a tremendous volume of condensate. And the condensate is highly corrosive. I've measured pHs below 2 in that mix, and so and it can be very, very odorous. So we need to manage that condensate. We also try to capture it upstream from the blower so that we don't burn the blower out. We destroyed a blower in a pilot project in about a month and a half, and it just ate right through it. So with negative aeration, whether it's a plus minus or strictly a minus or negative aeration, dedicated negative aeration system, we do have a biofilter attached.
Okay, the next question is, can moisture be introduced into the airflow?
It can, but not very effectively to where we are able to moisture condition the entire pile. You'll find that there's a wetting zone around the pipe itself, but because dry material becomes hydrophobic, that water does not transfer very well at all. And so where we find ourselves in a situation where piles do get dry, for example, in Utah, where we have an aerated static pile, 2 weeks, we're going to lose a tremendous amount of moisture out of that system. So a lot of operators will break the pile down at about the 2-week mark, move it into another bay, and moisture condition it as they go. But to answer your question, no, it's really not effective to condition the airstream going into the pile.
Okay, what field method do you use for measuring oxygen levels in the compost pile?
We have a probe that we insert into the pile that is attached to an O2 meter, and we draw air out from, my probe is 3 feet long, and so we insert it 3 feet, and we're sampling from the inner part of the pile. You will get oxygen transfer out at 12, 18, 24 inches. But once you get past that kind of outside zone, you'll be representing the pile as a whole. So we use an oxygen probe to do that.
Okay. How do you control the odors during the 30-day loading period?
With the example that I showed on the horse farm, first of all, horse owners and riders, there's a certain ambiance to the smell of horse manure, so they're not so concerned about that. Relatively fresh. When we're adding mix to the bin, we're adding fresh manure on top, and so we're really containing any of the anaerobic byproducts within the core of the pile. What we notice is when you start aeration, that first aeration cycle or two, you are going to be displacing pretty odorous gases off of that pile. But it takes only a cycle or two, less than an hour, for that entire system to become aerobic and to mitigate probably 80–90% of those offensive odors.
Okay. You indicated that ASPs used 55% less water when compared against windrows. Is that positive or negative pressure? Is there a difference between the two with regard to water needed?
Yeah, that number 55% was specific to that project in Tulare, California, and that was a positively aerated static pile situation.
Okay. This is a terminology question. What is paunch waste and what is night soil?
Great. Paunch waste is the partially digested feed in a cow's gut when he's been slaughtered. And there's quite a bit of it, and it can be really acidic and really stinky. Night soil is unprocessed human waste. In Beijing, China, because the city grew so fast and their sanitary sewer system is behind the times, shall we say, they have public restrooms with tanks, and a truck will come in, deliver water to the top of the building, used for flushing, and then pull the contents from the holding tank, and that is referred to as night soil. So it's unprocessed human waste.
What is the composition of the biofilter?
Biofilter is very much like the compost itself, but it tends to be a coarser media. It can be an organic media or synthetic plastic type material. Organic media is a woody, coarse material with a certain percentage of fines and compost, and the objective is for that mix to be wet. I should mention that too needs to be wet to function properly as a biofilter. There's a number of different design parameters that go into that, the gradation of the material being one. You want it to be deep enough such that your retention time is 30 to 40 seconds. So your airflow passing up through it takes 30 to 40 seconds to pass through the biofilter media. Synthetic medias will, and a biofilter, organic media will typically last 18 to 24 months before it needs to be replaced, whereas these plastic and polymer type biofilter media can last many, many years, 10 years or 15 years. They are also considerably more expensive.
Do you have any thoughts on emerging information that we are composting too hot, thus promoting more odors?
There's a real challenge. I call it the compromise of composting. As I mentioned earlier, if you are too hot, you are selecting a smaller range and decreasing the population of microorganisms that are doing the work. If you increase the airflow into the system as a means of cooling the pile down, basically what you're doing is displacing the heat out of the pile and replacing it with cooler ambient air, you also have the tendency to dry the process out. And if you get much below 50% moisture content, the whole thing comes to a screeching halt. Composting stops. So that's a bit of a compromise. With high temperatures, you can also emit higher levels of volatile organic compounds. So you are, it is desirable to keep that pile temperature down, 140, 150 degree range. The theoretical optimum for the biology of the system is between 110 and 120, but it's very difficult to do that with a lively substrate. And so we manage the pile temperature in an effort to compromise to the advantage of the operation. Every system is going to be different. The feedstocks, the size and scale of the operation, the climate of the facility, and so every system will take on its own nuances, its own personality, and you have to learn to work with it in that specific situation.
Are aerated bin systems being used for poultry, swine, or other livestock mortalities?
Yeah, they work great. They work great for that. The key is to make sure you don't overwhelm it with protein, particularly with the animal itself and the animal byproducts. We have a system at Stone Barn Center for Food and Agriculture in Tarrytown, New York, 4-bin aerated system where they are composting all the byproducts from chickens after the chickens have been harvested. So I call it the viscera, the beaks and feet, all the feathers, and they mix it in with horse manure and do that quite successfully. In fact, there's a 4-star restaurant within about 100 feet of the compost system, and of critical importance. They made me promise that we wouldn't stink up the place.
Have you done any work with thermal energy recovery on aeration systems?
Not formally, but I have kind of as a side hobby. And this winter, actually, I'm setting up one of our bin systems. It's going to be a hexagonal bin, and drawing heat off of it to heat my greenhouse. The folks again at Stone Barn Center have done this. They draw heat off of one of 3 micro bins to heat their seed trays in their greenhouse. And in fact, the same restaurant that I just mentioned, I think it's public knowledge at this point, but they were actually cooking food and serving it in their restaurant. I had chanterelle mushrooms that were cooked for 2 days using sous vide bags, but in our compost system.
Okay, I'll combine these 2 questions. They're related. Has to do with the 5-gallon bucket test for porosity and determining the bulk density of your pile as it's being built.
Okay, a cubic yard of material is approximately 200 gallons in volume. And so what we do is a simple protocol to fill a bucket half full, tap it several times, 8 or 10 times on the ground, fill it 2/3 full, tap it, fill it full, tap it, and then top it off. We weigh that bucket, and the weight of the bucket should weigh between 16 and 24 pounds, which is equivalent to 550 to 950 pounds. So if you have a 5-gallon bucket and a 200-gallon cubic yard, you simply multiply the weight of the 5-gallon bucket by 40 to get the equivalent of a cubic yard's worth of volume or weight. To determine the free air space in that same bucket that's been filled, we fill it now with water, weigh it. The difference in weight is the weight of the water, which we can calculate the volume to determine the percentage, 35 to 60% free airspace in that box. If anybody wants that, in the protocol for that, I've got it written up. Just send me an email. I'd be more than happy to send that to you.
Okay, we've come to the end of our allotted time, and so we're going to end the webinar at this point. Again, thank you for attending, and again, thank you, Peter, for this excellent presentation and answering the questions. Please join us next month on Tuesday, September 17th at 1:30 p.m. Eastern Time for our next Sustainable Materials Management webinar. Again, have a good day.